Welcome to CS1104 Computer Systems. This is the Unit 3 lecture part 2. During this lecture, we're going to revisit this idea of the ALU, or the arithmetic logic unit within the central processing unit of your computer system. And we're going to look at some of the basic design features of the ALU. This design of the ALUs are going to be very, very important for us to understand. Looking at and understanding the different kinds of functions that the ALU is performing is absolutely vital, because what we're going to discover is that those functions, those things that the ALU does, are essentially the capabilities of the computer itself. The only other things we're going to find that exist inside of the central processing unit is we're going to wind up finding that there is something called a program counter that's connected to the clock that just kind of is the heartbeat, if you would, the sequence of processing instructions. We're going to discover that we have some registers or places to hold stuff while we're waiting to get it into the ALU for processing. We know all of that stuff is kind of put together from a control perspective by something called the control unit. But when you get down to what's actually doing the computation, it's actually the ALU. So let's just look at the ALU for one moment. So ALU, or otherwise known as the arithmetic logic unit, is the thing that performs all of the arithmetic and logic operations that are able to be performed by the CPU. And essentially, we're going to get into looking at assembler language a little bit later in this course. And one of the things that we're going to find out is that all of the instructions within the assembler language for a particular CPU or a particular computer system, basically all they are is the functions that you can actually select within the ALU. Now, we looked a little bit before at this idea that I can use the multiplexer to select which functions are actually going to be performed, or in many cases, which functions output I'm actually going to allow to come out of the ALU. But essentially that becomes the foundation, if you would, for how we program the system. So the ALU is absolutely the most fundamental building block of the central processing unit, and perhaps the most fundamental unit of the computer system in general, simply because it is the thing that actually does all the computations. One of the things I had mentioned before is the fact that the adder is one of the most important functions that we have. So if I want to do something within a computer, the most primary function that I'm going to be able to do is add together two binary numbers. Now, we also know that when I convert one of them into 2's complement, that adder circuit actually becomes a subtractor circuit as well. So I can actually add some additional gates in front of my adder circuit. For example, I think we have to add a AND gate and a NOT gate in front of it. But once I do that, I actually can automatically convert one of the numbers into 2's complement, and my adder circuit then becomes a subtractor circuit. But either way, this is a key function within the system. By the way, many CPUs may actually have a logic circuit that does multiplication and division, but in simple CPUs, we might actually affect that by an algorithm. So an algorithm that takes advantage of our knowledge of addition, or perhaps leverages our ability to shift the bits by adding one to it. All of those kinds of features. So very, very low level what we're doing in the CPU. We just take those simple instructions and combine them together to become more sophisticated operations within the computer. So one of the reasons why they have to be so fast is because I need to do a lot of these very simple operations to get to my the modern programs and program capabilities that we have today. Again, looking here at adder subtractor functionality. And again, like I said, basically all I have to do to make an adder into a subtractor is I would essentially invert the number coming in and then add one to it. So think of it this way: to make a subtractor circuit, all my inputs coming in on the B side, for example. What I want to do is I want to invert them, because that gets me to 1's complement, and then I have an adder circuit that adds 1 to it. And from there, if the output goes to the adder circuit that adds to the A number. So essentially, that's all a subtractor is. One way that I can actually effectively do it. Shows us a very idealized, simple example of an ALU where I have an A input, a B input. And by the way, the ALU always is going to operate on 2 inputs. And maybe I have, I'm going to add 2 numbers together. Maybe I'm going to subtract 2 numbers from each other. Maybe I'm going to do a bitwise or perhaps an increment, which means I'm just going to simply add 1 to the number. Basically, it's always going to have these 2 inputs. These inputs generally are going to have a register associated with them, so you're going to see this coming up again and again. But what we find is I'm going to have some addition subtraction capability, which is one of the most important things we do. I'm oftentimes going to have an AND circuit, which is just going to do a bitwise AND of the 2 numbers, A and B. And I might have a bitwise OR circuit in here as well. I select those using a multiplexer. So I can use the select bits to turn these things on or turn them off. A lot of times what's going to happen is ALUs are structured in such a way that I might have the output of one of these circuits become the input to another. So I can actually combine the add subtract with perhaps an AND to create new kinds of functions. And again, back to this same picture, give you that view of, just the basic components. 2 numbers that I'm bringing in, usually going to be prefaced with a register. Okay, so maybe you have a register for A and a register for B here. In the ALU that we're going to use, I think we're going to be having an A register where we normally bring things in, and then we're going to have a D register for data. But essentially that same structure you're always going to have. In this particular case, I have an add and a subtract circuit, a shift, an AND, which is a bitwise AND and OR, and I may have additional ones. And I could in fact have an AND circuit with something that I either turn on or off with a small multiplexer to have multiple operations that could be performed on it. And in fact, when you look at the ALU that we have in our book, that's what it's going to do. And I control all of that with the multiplexer. So the multiplexer, basically, I select which output I want to actually